On the bell work, it says in a survey of 607 general surgeons and orthopedic surgeons indicated their major professional activity. The results are summarized in the table above. If one of the surgeons is selected at random, which of the following is closest to the probability that the selected surgeon is an orthopedic surgeon, which indicates professional activity research? Okay, that their professional activity is research. Sorry. So hardest part about this question is really just finding out the information. We don't really want to get dismayed by this total box because that really doesn't affect us too much. The number that we're going to care about is 607 right here. We want to find orthopedic surgeons that specifically say they do research. So that's 74. So this probability really maps to the percentage of the doctors that are orthopedic surgeons that specialize in research. So in order to find the probability, what we would take is we would take 74 divided by 607. You plug that into a calculator, and I believe you get 1.1219. That gets rounded up to approximately 0.122, which should correspond to answer A on the bell work. So nothing terribly difficult, just how you analyze the graph, right? You only want to pay attention to the parts that are necessary. Okay, we don't want to get drowned out by the word problem and get lost in the words, or really be focused on a different area of the table that isn't as important to you. Okay, here's your 5-minute check over lesson 9.4. It says the terminal side of an angle theta in standard position intersects the unit circle at point P, which is 3/7, and then 2 square root of 10 over 7 for the y value. Find sine of theta and cosine of theta. Remember that your unit circle is the key term here. Okay, on the unit circle, that means our R value is 1. Okay, so the R value is 1. I draw it real quick. Have a radius, R value is 1. This point is 1, 0, 0, 1, negative 1, 0, 0, negative 1. Given this, saying that the terminal side will intersect, and we have the 0.372 square root of 10 over 7. Okay, because the R value is 1, and we know that cosine of theta is equal to x over r. Since the R value is 1, standardized, the x value really is the cosine value. So we can say that the cosine of theta in this case is 3/7, because it would be 3/7 over 1. Okay, sine of theta is equal to y over r. And since our R value is 1, once again, we can say that sine of theta is equal to 2 square root of 10 over 7. Okay, very specific because the R value is 1. Therefore, our x value becomes our cosine value, and our y value becomes our sine value. Okay, we got another one. Terminal side of angle theta in standard position intersects the unit circle at point P, negative square root of 2 over 2, and square root of 2 over 2. Find sine of theta and cosine of theta. So once again, this one's going to map to our x value and our y value. So it looks like it should be answer B, because cosine of theta is going to be x over r, r being 1. So cosine of theta is negative square root of 2 over 2. And sine of theta is square root of 2 over 2 for the same reasons as the first problem. If anybody wants to know, this angle is actually 45 degrees. Okay, it's one of your perfect squares or perfect triangles in terms of trig ratios with a 45, 45, 90. Connor, you taking notes or you sending Snapchats, buddy? All right, not taking notes yet. I'll take it. So the next one. It says find the exact value of sine of 225. Remember, the first thing that we want to do here is we want to figure out where exactly it falls. So I'm just drawing my axes and labeling them. So that is 225. That glare is pretty bad. Slide this bad boy back. See if that helps. Did that help the glare at all? Yeah, it did. A little bit. Okay, so we got 0 to 360, 90, 180, and 270. We rotate 225 degrees. So that puts us in the third quadrant. That angle is 225. We can find our reference angle by taking 225 minus 180. That gives you 45 degrees. That corresponds to this angle theta right there. There's our right triangle. Okay, and it's asking for sine. Remember, all trig ratios are positive in quadrant 1. Sine and cosecant are positive in quadrant 2. Tangent and cotangent are positive in quadrant 3. And cosine and secant are positive in quadrant 4. So the cosine or the sine of 225 is equal to the negative sine of 45 degrees, okay, because our reference angle is 45. Sine of 45 is square root of 2 over 2. So the sine of 225 is equal to the negative square root of 2 over 2. Just like that. Okay, on the next one. It says determine the period of the function graphed at the right. Okay, and it looks like we have this little M-looking graph, but we want to be careful and make sure that we encompass a full period. So when does it actually repeat itself? So here we have a positive slope. We don't really want to take a guess at what that slope is, but you can see it's kind of leveled off. Then it has a very sharp decrease, but then it has a deep increase, right? Some people would say that this is a period, but we have to understand that this section right here differs from this section right here. And then it repeats itself. It's kind of like an M value, okay? And it looks like it breaks between pi and 2 pi. We can't find an exact value. We just have to assume what's going to be closest one. So if we're looking, 2 pi is right in the middle of this break. So that's like 2 1/4 periods. Pi is at this high point. So once again, we're not encompassing this section. 3/4 pi is less than pi, which would be right about here to our min point. And 3 pi over 2 is the only one that splits. It's going to roughly be right about there. So based upon the information that we can give us, the closest one is 3 pi over 2. Okay, periodic functions are going to be key because all of your trig functions are periodic. They repeat themselves over and over and over again. Okay, last one. If x is a positive acute angle and cosine of x is equal to 7/9, what is the exact value of sine? So if I draw it up, cosine is y or x over r. So we need to find my y value right there. So we have to first reverse the Pythagorean theorem. Okay, we got 9, 7. We're trying to find this side because sine is y over r. So reversing the Pythagorean theorem, r is 9 squared. R is 9, so Pythagorean theorem says you're going to square it. Is equal to 7 squared plus y squared. 9 squared is 81. 7 squared is 49 plus y squared. 81 minus 49 is equal to 32, so that's equal to y squared. Take the square root, and we get y is equal to the square root of 32. This is where the power product of radicals has to kick in. We want to find the largest, biggest square, perfect square that goes into 32. That is 13 or 16. Man, I need to step my game up. So square root of 32 by the power product of radicals can be broken into the square root of 16 times the square root of 2. Square root of 16 is 4. Square root of 2 can't be simplified, so that's 4 square root of 2. That is our value of r. Take sine of theta, right there, y over r is 4 square root of 2 over 9. Done and done. I think that was actually close to 5 minutes. Whew. A lot of talking now. Okay, so we have examined periodic functions. What now we're going to do is we're going to describe the graph and graph sine, cosine, and tangent functions. Okay, we're going to describe and graph the other trigonomic functions. Okay, so more or less, this breaks into reciprocal graphs, sine and cosine graphs, and tangent. Okay, if we think about it that way, we're going to be all right. So, first, there is a general form for each one of these trig functions. Okay, it can be written as this: y is equal to a times the sine of bx plus c on the inside plus d, where b is the coefficient of your variable. Sometimes you'll see it written like this: a times of sine of b x plus c, or theta plus c plus d. I don't know why I put 9 up there, plus d. Okay, just understand that b is factored out. It's what's known as the periodic factor. Okay, similar to your polynomial functions, each one of these has a key thing. First, a is the amplitude factor. Okay, that's where the amplitude comes from. We'll talk a little bit more about that. B is your period factor. C and D, so C is what's known as your phase shift. And D is your vertical translation. Okay, for a cosine graph, it'll work the same way. It's A times the cosine of bx plus c plus d. Once again, you'll see it written as this, with b factored out. But once again, all of them have the same impact. A is always your amplitude factor. B, whether it's on the inside or the outside, it is your period factor. C is your phase shift. Okay, we'll generally be dealing with the format of the second one. So your phase shift, you can look at it as a plus. We're shifting it to the left. Negative, we're shifting it to the right. And D, vertical translation, shifting your graph up and down in terms of the midline. Okay, very important to know those. So make note of them now.
She just asked me to come back at 2 because she's on her meeting ran long. I agree.
That's what I say to that. I say, I'm mature, huh? I mean, mature of me. I understand getting pulled into a meeting, but nobody likes that. Nobody likes it. Okay, hopefully you guys got that stuff down so far. All right. So the first graph we're going to talk about is just y equals the sine of theta. Okay, believe it or not, all of these coefficients are still represented. Just a is 1, so it's 1 sine of theta. B is also 1. C would be 0. D would be 0. Okay, we would incorporate those, but in mathematics that's redundant. If you're multiplying by 1, it stays the same. And if you're adding 0, it stays the same. So those are omitted. Okay, the sine function. Right here. Okay, this is 0, 0, 0. It's going to start there. This is 90, or pi over 2. 180, or pi. 270, or 3 pi over 2. 360, or 2 pi. Okay? First thing we have to be very clear on is what I'm going to draw up is one cycle. Okay? One cycle of the period. That means that it repeats itself every 360 degrees, or every 2 pi radians. Okay? If you think about that, that makes sense, because if we have an angle in standard position, rotating 360 degrees is rotating all the way around. Okay, or rotating 2 pi is rotating all the way around. At that point, then it begins to repeat itself. Okay, has to deal with coterminal angles. Okay, the sine function will always start on what's known as the midline. Okay, in its standard position, that is the x-axis. Okay, it'll always start on the midline at 0, 0. Okay, or one cycle will start at 0, 0 in its basic form. Then it'll go to its high point of 90, which is 1. Then it'll go to 180, back down to the midline. 270, it'll hit its minimum. And then 360, it'll hit the midline again. And it looks something like this. Okay, and if you think about this logically, we know that sine of theta is equal to y over r, right? So if I just draw up my standard position from using the points 0, 1, 1, 0, negative 1, 0, and then 0, negative 1, and we were to take the sine. If you notice, these are all your quadrantal angles, right? An angle of 0 hasn't left the positive x-axis. So our value of y, or our value of r, is equal to the x value, because it extends that way, right? Sine of 0 is 0, y over r, 0 over 1. Sine of 90 is 1, because our r value matches our y value. Okay, sine of 180 is 0 again, because the r value matches the x value, because the radius doesn't change of the circle. And then sine of 270, or 3 pi halves, is 0 as well, because it's y over r, or it's negative 1, I apologize. Negative 1, because we end up with negative 1 over 1. R is always positive. And then we're back to 360, or 0, where our y value is 0. Okay, this is a very, very key thing. You can break it down and graph this by finding the location of those specific points. Okay, that's what's known as x scales. These are critical points. Where it touches the midline, it's maximum, midline, minimum, midline. Okay, in this case, our midline is our x-axis. So where it touches the midline are our x-intercepts. Okay, so I'll give you a second to copy that down. Pretty simple, pretty easy. Okay, you should know how to do this in radians as well. Okay, degrees, radians, they're interchangeable. All right. Got it? Perfect. Okay, so now we're talking cosine. Okay, the first graph, or the parent function, is y equals the cosine of theta. Once again, you could fill out all of these variables, but it's redundant. The value of A is 1, value of B is 1, value of C is 0, and the value of D is 0. Okay, if we remember that cosine of theta is equal to x over r, okay, and we use our unit circle, we can help place these out. Okay, there's my midline, There's 90 or pi halves. There's 180 or pi. There's 270 or 3 pi over 2. And there is 360 or 2 pi. Very similar to sine, cosine also repeats itself every 360 degrees or every 2 pi radians. And if we actually plot these using our little key here, so that is 1, 0, that is 0, 1, negative 1, 0, that is 0, negative 1. Looking at the quadrantal angles, knowing that cosine is x over r, at 0, we have a 1, right? Our x value matches our r value. So at 0 and 360, our cosine graph begins at the maximum. Okay, then we rotate 90 degrees to the point 0, 1. Okay, cosine is x over r, so that's 0 over 1, or 0. Touches its midline. Okay, at 180 degrees, we use the value negative 1 over 1, which gives us a negative 1. 270, we're back to the y-axis. So it's 0, negative 1. Cosine is the x value, so cosine is going to be 0. And then we're back to 0 or 360, where we had our maximum. Okay, and once again, this is one cycle. If you think about it, cosine and sine are the exact same graph, just sine is shifted 90 degrees to the left, or cosine is shifted 90 degrees to the right. However you want to look at it that way. Because this also carries on, it's periodic. So if I were to go to a negative 90 right here, or a negative pi halves, I would end up back on my midline right there. And you can see that looks like the sine function just shifted 90 degrees to the left, or 90 degrees to the right to get to the cosine function. Okay, I'll give you a second to write that stuff down. B is the period factor. All right. So how do these relate to the new vocabulary that you're going to have? Okay, first one is amplitude. Okay, amplitude is the distance from the midline to its maximum or minimum. Okay, so you can see the maximum here is at 1. The minimum's at negative 1. The midline splits those exactly. Okay, so our amplitude here for the original cosine and sine functions, the amplitude is 1. Okay, the distance from the midline to the max, or the distance from the midline to the min, is how you define amplitude. Okay, and it's by the absolute value of the A variable. Okay, frequency. Frequency is how many times does it complete a full cycle within a given period, okay, or over 1 unit, however you want to look at it. 1 unit is typically defined as 360 or 2 pi, okay, 1 circle rotation. The cosine and sine and its base function commits 1 cycle per one period, therefore it has a frequency of 1 to 1. Okay, sometimes they'll give it to you in what's known as hertz. Hertz is cycles per second. Okay, and you'll see that your frequency is the reciprocal of the period. And I'll show you how to find that as well. All right. Now you get the book's version of the graphs. Okay. There you go. It explains the domain as being all real numbers. The range is from -1 to 1. The amplitude is 1, and the period is 360 or 2 pi. Okay, and it has sine to the left and cosine to the right. Okay. And you can see that it's continuous all the way through. There's no asymptotes or anything like that, like there will be with secant and cosecant and tangent and cotangent. It's pretty simple. Okay. So find the amplitude in the period of y equals 1/3 sine of theta. Not 1/3 sine, sine of 1/3 theta. Okay. So we're given our graph, right? It is y is equal to sine of 1/3 theta. Remember, we have the general form of A times sine of B theta minus plus C plus D. Okay, and we're going to go through and graph this because you find all of these things in order to graph it. Okay, and graphing these breaks down into 5 different steps. First thing that we're going to talk about, amplitude. Okay, amplitude comes from the absolute value of A. Okay, so in the equation that we're using, sine of 1/3 theta, the A value is 1. It's omitted because it's redundant. So here, it's the absolute value of 1, or just 1. That's the distance from the midline to its maximums. Okay, the next thing we're going to talk about is the period. Okay, period is found by taking the general form, taking 360 divided by the absolute value of B. Okay, understand that this is in degrees. If it was in radians, the period would be found by taking 2 pi divided by the absolute value of B. Okay, both equations work. Here we have a value of 1/3 for B. So it's 360 divided by 1/3. Anytime you're dividing by a fraction, you flip to its reciprocal and multiply. So this is really 360 times 3/1, which is equivalent to 1080 degrees. Okay, so that's how long it takes for it to actually complete a cycle. 1080 degrees. Okay, the next thing, we want to find the location of our critical points, our x scales. Okay, we can find this by taking the period that we just found and dividing that by 4. Okay, so 1080 divided by 4, 250 makes 1,000, 270? 270 degrees. Double check myself to make sure I'm right. Okay, yep. So this is the location of my critical points. Where it touches the midline, where's the maximum? Where it touches the midline, where's the minimum? Where it touches the midline again. Remember, we're dealing with the sine function, so it starts on the midline. Okay, then we would go to the phase shift, which our value of C is 0. So there is no phase shift. And then we go to the vertical translation, which comes from the value of D. That moves the midline. That, once again, is 0. So we don't have a phase shift. We don't have a vertical translation. We didn't adjust the amplitude at all. All we did was extend this period, and we're going to use that to find our x scales. So to draw our graph, it would be 1, It's a negative 1 because our amplitude is still just 1. Our x-axis is our midline because the graph isn't shifted up at all. Okay, the starting point for sine is still on the midline. Okay, and now we have the location of our important points. So every 270 degrees is where we hit a quadrantal angle. So that's 270, 540, 810, 1080. Okay, so if I wanted to graph my sine function, I know it starts on the midline and then goes to its maximum. So I go to my maximum of 271. I go to the midline at 540. I go to its minimum at 810. And I go to its minimum at 810, and then back to the midline at 280. Draw my graph. That is what the graph would look like. The question did not ask us what to graph. Okay, the question asks us what is the amplitude and what is the period. Okay, so for this question, since the amplitude factor is still just 1, it is only 1. The period for this question, because we had 1/3 for B, makes it 1080. And I'm walking you through how to graph it because at the end of the day, that's the main goal. We're going to be graphing these bad boys. So first, find the amplitude. It's the absolute value of A equals the absolute value of 1. So it is 1. Period. Take 360 divided by the absolute value of B. Our value of 1/3 is for B. So that's 1080. So the amplitude is 1 and the period is 1080 or 1080 degrees. You'll find that if you have a decimal for B, the graph has been extended. Okay, the period's been lengthened. If you have a whole number for B, the graph has been compressed. Okay, so find the amplitude and the period for y equals sine of 1/2 theta. Okay, did we adjust anything for A? No, the answer to that is 1, right? Because it's still 1 times the sine of 1/2 theta. What we did adjust is B, okay, by a factor of 1/2. So our amplitude is 1, so we can eliminate answers C and D. To find our period, once again, what you do is you take 360 or 2 pi if it's in radians, divided by the absolute value of B, so 360 divided by 1/2, which in all reality is 360 times 2/1, because we flip to its reciprocal and multiply, which gives you 720 degrees. Okay, so this one should be answer A. Amplitude of 1, period 720. Okay, graph sine and cosine functions. Okay, graph the function y equals the sine of 3 theta. Okay, so we're going to break it down the same way that we just did. Okay, we're going to find the amplitude and the period first. And we're going to talk if there's any phase shifts or vertical transformations or anything like that. So amplitude, once again, absolute value of A. Our A value is 1, so that equals the absolute value of 1 or just 1. Okay, the period equals 360 divided by the absolute value of B. Okay, B is 3, so that's 360 divided by 3, which is equal to 120 degrees. That is your period. The x scales. Take the period you just found, 120 degrees, divide that by 4, and you get 30 degrees. Okay, that's the location of your critical points. Phase shift. Your value of C is 0, so there is no phase shift. Vertical transformation, your value of D is 0, so there is no vertical transformation. All we did, once again, is adjust the period with an amplitude of 1. Okay, so we go from 1 to a -1. Our midline is still the x-axis. We're starting at sine. My x scales say that I need to have a critical point every 30 degrees. So that's 30, 60, 90, 120 is one whole period. Sine starts on its midline, which is the x-axis, goes to its maximum, back down to the midline, then to its minimum, back up to the midline. There you go. And this would actually repeat itself, right? You could extend it out to 2 periods. 150, 180, 210, 240, maximum, midline, minimum, maximum. Just like that. Here's the first period at 120 degrees. Here's the second period, 240 degrees. If you get into that process, finding amplitude, period, x scales, phase shift, vertical translation, this is pretty simple. Okay, so find the amplitude, period, and x-intercepts. A is equal to 1 and B is equal to 3. Amplitude is 1, so the maximum and the minimum is 1 and -1. The period factor was B, so once we plug it into our period formula, we get 120 degrees. So one cycle has a length of 120 degrees. The x-intercepts are 0, 0. 1/2 of period. I just remember that it goes to its maximum and then back to the midline. So you can see our first maximum is at 30 degrees. Our first intercept or midline is at 60 degrees. Then we go to the midline of 90, or we go to its minimum at 90, and then we go back to the midline at 120. I say midline rather than x-axis because in the next section, these bump up and down. Okay, it's just very important to realize that sine and cosine, their basics is the x-axis is the midline. Okay, but as we add factors of D and C, that midline is going to change. It's going to shift up, it's going to shift down. Okay, so it's just important to get your mind trained thinking that way. Okay, so here, graph the function y equals 1/2 cosine of theta. Okay, same exact process, although instead of sine, we're using cosine. Okay, vertical translation. Okay, starting with the amplitude, we have 1/2 cosine of theta. So amplitude factor has changed now. Okay, amplitude comes from the absolute value of A, which in this case is equal to the absolute value of 1/2, which is equal to 1/2. That means instead of going all the way to 1 and -1, it's going to 1/2 and -1/2. Amplitude is the distance from the midline. Okay, the period. There is no element of B, so it is still 360. There's your equation, 360 divided by the absolute value of B. So that's 360 over 1 in this case, or just 360. Your x scales, take the period you just found, divide it by 4, and you get every 90 degrees. Phase shift comes from C. There's no element of C, so there's no phase shift. Vertical transformation comes from D. There's no D, so nothing happens again. So we stayed on the x-axis. We didn't adjust the period. We just compressed this graph a little. We're dealing with cosine of theta. So now instead of going from 1 to a -1, I go from 1/2 to a -1/2. My midline being 0. Okay, my x scales say that I have a critical point every 90 degrees. So I label that on the x-axis. Okay, cosine of theta begins at its maximum. Then it goes to its midline. Then it goes to its minimum. Then it goes back to its midline. And it completes the cycle at the maximum. Going from 1/2 to a -1/2 for maximum and min, because the only thing that was adjusted is the amplitude factor. Okay, if you get into the process, like I said, these are pretty simple. The hardest thing is remembering where does cosine and sine begin, really. Okay, so the graph is compressed vertically, so the minimum or the maximum is 1/2 and the minimum is 1/2. Okay, the period can be found by taking 360 divided by the absolute value of b. The x-intercepts are the location of the critical points. Okay, like I said, if you remember that cosine starts at its maximum, then to its midline, to its minimum, to the midline, to the max, and sine starts on the midline and goes maximum, midline, minimum, midline, it's a pretty simple, easy process. That's fine, Kai. I'll record it. The recording is going to be up there late tonight. I have a basketball game, so I'll get it up there as soon as I possibly can. Hopefully I can finish this early to actually start the process, and you should see it on my YouTube channel. Feels weird saying I have a YouTube channel, I'm not going to lie. Okay, so graph the function y equals 2 sine of 2 theta. So in this case, if we think about what's actually happening, if we just analyze, did A change at all? No, still just 1. So our graph should go from 1 to -1. So from here, we can eliminate B, right? We know it can't be B. Okay, this sine of 2 theta, that gives you an element of B. So if we plugged it into the period formula, where we take 360 divided by the absolute value of B, this would be 360 divided by 2, which states that it should complete its period every 180 degrees. So we're looking, where does 1 end at 180 degrees? C completes a period at 360. D doesn't even complete a period by 360. A, there's 1 period at 180 degrees. There's 2 periods at 360 degrees. Okay, so nothing changed amplitude-wise, and nothing changed vertical translation, phase shift, anything like that. It's just they've adjusted the period. Once again, if you have a whole number for B, you'll notice that the period gets compressed. If you have a fraction or a decimal for B, the period is expanded. Connor, am I boring you, buddy? All right, as long as you're not paying attention to too much stuff. Okay, so this one again, pretty simple, pretty easy. What happened to A? Well, it's been expanded, right? So now it's the absolute value of A, so our graph should go from 3 to -3. Okay, so that eliminates C, D, and B, simply because we know that A. The period factor, we take 360 over the absolute value of B to find that it completes a period every 180 degrees. There's 1 period at 180. There's 2 periods at 360. Therefore, the answer to this question is A. All right, here's where it can get a little tricky. Humans can hear sounds with a frequency of 40 hertz. Find the period of the function that models the sound waves. Okay, hertz by definition is cycle per second. A cycle per second. And your frequency is the reciprocal of the period. Okay, so if our period is found by taking 360 divided by the absolute value of b, the frequency would be b absolute value over 360. Okay, because that's our period formula. If we flip it, we get the reciprocal of the frequency. Blah, 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 blah. Okay, so what this is telling you is because it's hertz, it says 1 cycle per second. So that means if we were to switch this and get it to its actual frequency, it would be 1 over 40 or 0.0025. Okay, frequency is cycles per second. So that means that this completes, the period would be 1/40th. It's 40 cycles per second, the period of times it takes for one cycle. So the period is 1/40th, or about 0.25. Okay, so because it was given 40 hertz cycles per second, we'd flip it to its reciprocal to find 1/40th. Okay, the next one. Humans can hear sounds with a frequency of 40 hertz. Let the amplitude equal 1 unit and write a sine function to represent the sound wave y as a function of time t. Then graph the equation. Okay, so we have the same frequency, it's 40 hertz. So if we set this equal to our period, which is 360 over the absolute value of b, we're trying to find the period factor. Okay, so we're trying to find b. We have to solve this equation. All of your frequency questions are handled exactly like this. Okay, you can cross multiply. So b times 1 is equal to b, or the absolute value of b. 40 times 360 Okay, so b is equal to 14,400. If we write this into a sine function, because the amplitude is still 1 from the question, it would be the sine of 14,400. Oh, they do it in, you jerks. You jerks. They did it by radians. I don't know why they did that, because everything they've done so far is in degrees. But you can see with it being in radians, it's the same concept. 0.025 or 1/40th. So, and then you'd multiply to bring it over, divide, and you'd get that the b value is 80 pi. I don't know why they did that, because they've done everything else in degrees. 80 pi is equivalent to 14,400. Jerks. Okay, and then they're just putting it in. The amplitude factor they gave us is 1. The b factor is good. There you go. I've lost a lot of kids. You know, you guys complain that you need help and then you don't stay on for the lecture. That's kind of frustrating. Okay, the bass tuba can produce sounds with a frequency as low as 50 hertz. Find the period of the function that models the sound. So that would be 1/50th, which would be 0.02. Okay, this one's going to be C, 100 pi, sine of 100 pi, and that's because they set it up as 0.2 times is equal to 2 pi over b. They multiply by b on both sides, and 2 pi times, or divided by 0.2 or 2 times 50, however you want to look at it, is equal to 100 pi. I'm not worried about the frequency stuff because you don't have any of those. Tangent function. Okay, tangent where it gets a little interesting. Okay, it is still a periodic function, but it has a period of 180 degrees. Okay, you can also see that it has undefined areas. That's these dotted lines on the asymptote. Okay, and if you're looking at it, it kind of makes sense. Okay, once again, it's going to fit the same format as our general equation. Okay, where it's A times tangent of B theta plus C plus D. D is your period factor, A is your amplitude factor. Tangent, since it goes from negative infinity to positive infinity on the y-axis, amplitude factor is pretty null and void. You're really only dealing with B, C, and D. Okay, but tangent, as we know, tangent of theta is found by taking y over x. So if I draw my little quadrants again, points 1, 0, 0, 1, negative 1, 0, 0, negative 1. Where is y over x? Okay, here we have an x value of 1 and a y value of 0. So tangent of theta would be 0 here. But here, it's 1 over 0. So it's undefined. Okay, this also 0. And then at the bottom y-axis, y over x gives you undefined. Anytime that the tangent function is at 90 or 270 degrees, you hit an undefined point, and that is where you have your asymptotes. Okay, but there is no other limits to the range. So parent function y equals tangent of theta. The domain theta cannot equal 90 plus 180 in. That means every 180 degrees, so 90, 270, 450, we have an asymptote. That's where it becomes undefined. Okay, the range, all real numbers. The amplitude is null and void because it expands from negative infinity to positive infinity and continues to increase. The period is 180 degrees, and the intercepts in one cycle happen at 180 in. So that means you have an intercept at 0, 180, 360, 540, and so on. Okay, once again, it goes periodically. That one period is between two consecutive asymptotes, and then it repeats itself. So every 180 degrees. So here we're really just focused on finding our intercepts and the location of our asymptotes. Okay, so find the period of y equals tangent of 1/2 theta. Okay, there is no amplitude factor. So, but we're going to treat it the same way. That way you guys can get in the habit. Amplitude for tangent is null and void. The period in this case is equal to 180 divided by the absolute value of b. Helps if you can see me write it. So the amplitude is 0, and we're working with tangent 1/2 theta. Okay, the period is 180 over b, the absolute value of b. So this is really 180 over 1/2. Flip to its reciprocal and multiply, and you'll find that the period happens every 360 degrees. Okay, this is a useful thing. Okay, because this tells you the location of your asymptotes and where your intercepts are. Your phase shift is still 0, and your vertical translation is still 0. Notice that I didn't label any critical points because X scales in this case don't necessarily work. Okay, we have to remember that the base graph of tangent crosses through the origin. Okay, it goes through the point 0, 0. So What that means is that I have an asymptote at 180 degrees. Okay, and then I'm going to hit 360. I'm going to have an asymptote at negative 180. I'm going to have another intercept at negative 360. Draw my asymptotes like this. There's my graph. There's that side of it. There's that side of it. So the period's been lengthened. So the period is 180 over B, which is 360. The asymptotes, okay, 180 divided by 2B. It's just simpler if you remember. Okay, or what you can do, an easier way to find this that I don't think I explained. Okay, to find your asymptotes, okay, your period or your x-intercepts is always done by taking 0 plus the period, however far. That gives you your location of the of blah, 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 blah. Your x-intercepts. Your asymptotes, an easier way to find it because I didn't write it down. I went over it fast. Asymptotes. If I take whatever's on the inside here, okay, so this 1/2 theta, and I set it equal to 90, and if I set it equal to negative 90. Now, why would I do that? That is because that is the origin or the places of our original asymptotes. Okay, and then I'm going to solve for theta just like I would. So I'm going to divide by 1/2 on each side. 90 divided by 1/2 gives me theta is equal to 180 degrees. That's the location of my first asymptote. Okay, on the positive side, 1/2 theta set equal to a negative 90. Solve for theta again by dividing by 1/2. That gives me theta is equal to a negative 180. Okay, and then if I add my period to each one of these, so 360 plus 180 means I have an asymptote at a positive 540 degrees. Negative 180, subtracting 360 gives me a negative 540. That's my next asymptote. Forgot that part. It's okay, because I do that in my head. That's the easy way to do it. Set whatever's on the inside, or your B plus C, set it equal to 90, and solve for theta. Hopefully they'll give me another one. Yep. 180 degrees was an asymptote, 540, 900, and you'll notice that there's 360 degrees between those. 540 minus 360 is 180. Okay. Your x-intercepts are done by taking 360 plus whatever your origin, which is 0, 0. Okay, so find the period of y equals tangent of 3 theta, then determine the asymptotes. I'll go through this one a little bit better because I messed it up on the last one. And okay, no phase shift, no vertical translation again. No amplitude, we'll just do period and asymptotes. So period found by taking 180 divided by the absolute value of b for theta. And we are working with 3 theta. Okay, so my value of b is 3. 180 divided by the absolute value of 3 is equal to 60 degrees. Okay, that is my period. Okay, now to find my asymptotes. Okay, like I just did, I'm going to take what's on the inside, this 3 theta. I'm going to set it equal to 90. Okay, and then I'm going to solve for theta. Which gives me theta is equal to 30 degrees. Okay, and then 3 theta set equal to a negative 90, because I got to find the negative asymptote. Divide by 3. Theta is equal to a negative 30. So what this means, because there's no phase shift or anything like that, means that if my graph starts at the origin right here, I have an asymptote at 30 degrees and negative 30. Okay, and then they reoccur every 60 degrees. So 30 plus 60 is 90. That's the location of my asymptote. Okay, and I use my period in conjunction with these to find it. On the negative side, if I subtract the period again at negative 90, okay, so intercepts. Starting at the origin, if I add the period and subtract the period, I get 60 and negative 60. So my graph of this tangent would look like this, with my asymptotes occurring at 30 and negative 30, and then 90 and negative 90, and then 150 and negative 50, 150. The intercepts at 0, 60, 120, 180, and so on. All right, period 60, asymptotes of negative 30, 30, 90, and so on. Okay. Time for the fun ones. Cosecant, secant, and cotangent. Okay, for cosecant and secant, it's much easier to think about graphing a sine and cosine function. Okay, for tangent and cotangent, it's easier to think about graphing the reciprocal of it. Okay, what we have to realize is that these reciprocal functions, like cosecant, if I wanted to graph cosecant of theta on a calculator, I would have to enter 1 over the sine of theta. Okay, that's equivalent to cosecant of theta. So what does that mean? It means wherever I had an x-intercept on sine, I now have an asymptote. Okay, if I'm looking at the secant function, that's 1 over the cosine theta is equal to secant of theta. So wherever I had an x-intercept for cosine, I now have an asymptote. Okay, cotangent of theta is now 1 over the tangent of theta is equal to cotangent theta. So wherever I had an x-intercept for tangent, I now have an asymptote. Okay, and you can see it because the way that we're going to do this is we're really going to graph those sine and cosine functions, and then we're going to draw our secant and cosecant. So here's cosecant. It's the reciprocal of sine. You can see your sine functions here. Okay, they have an intersection point at the maximum and the minimum. Wherever there would be an x-intercept for sine is now an asymptote. Okay, so the range is from 1 to a positive infinity and from -1 to a negative infinity. Continues going down. It does not go into this area of -1 to 1. Okay, it's the reciprocal of sine. Secant of theta, the reciprocal of cosine, right there. Okay, you can see once again it has the intersection at the maximum and the minimum. Does not touch in between 1 and -1 for the range. Okay, cotangent of theta, the reciprocal of tangent. So your tangent is red dots right here. You can see that tangent would normally have an intercept at 180 degrees and 0 degrees, but now it has an asymptote. Okay, and rather than starting low and ending high, it starts high and ends low for cotangent. Okay, very important graph. Make sure that you view it. Okay, I got like 5 minutes left and I'm going to turn you loose. Hopefully 5 minutes left. Okay, find the period of 3 cosecant of theta, then graph the function. Okay, same thing. This is cosecant, so we're really graphing 1 over 3 sine of theta. So we're approaching it the same way. Okay, so I'm going to focus on graphing this sine function first. So I'm going to do it the same way that I would. The amplitude comes from 3, so my amplitude is 3. That gives me the location of my minimum and maximums. The period, once again, is 360 divided by the absolute value of b. B is 1, so my period is 360. My x scales is 360 divided by 4, or 90 degrees. Okay, no phase shift, no vertical transformation. Okay, so I'm going to start off by graphing this sine function. It goes from 3 to -3. Okay, no vertical transformation, so I know that I begin on the x-axis. Okay, so 90, 180, 270, 360 coming from my x scales. My sine function starts here, then it goes to its maximum, then it goes to midline, then it goes to its minimum, then it goes back to the midline. Okay, in purple, this dashed graph is what my sine function would look like. Okay, but I'm accessing the secant function, okay, or 1 over 3 sine of theta. So I'm going to do that in red. Wherever I would have an intercept or an x-intercept for sine, I now have an undefined. Okay, I now have an asymptote. Okay, I intersect at the maximum and the minimum, going like this. Okay, the period did not change. The amplitude is 3. Okay, but that's the way you want to approach it. You graph sine and cosine, and then you graph secant and cosecant. Okay, so the amplitude of my sine function was 3. So that gave me my maximum or my minimums. You can see wherever there was an intercept on the sine function is now an asymptote for the cosecant function. Okay, find the period of y equals 4 secant of 2 theta, then determine the asymptotes. So the period, once again, found by taking 360 over the absolute value of b, that's going to give you 180 degrees. Okay, the amplitude is 4. It's cosecant, or it's secant, so it's the reciprocal of cosine. So we should have asymptotes at 45, 135, 225. That's all I got for you. Perfect, just in time. Okay.